Okay, so yes, math for life. I'm doing math so hard, my pen exploded. So to give you a little context, I wanted to show you a wonderful time suck, if you have not found it yet, called XKCD, which has scientific comics. And here is one of my favorites relating to mathematics. As you can see, we have sociologists, psychologists, biologists, chemists, and physicists, all of who believe they are the most pure basis of what we are studying. But as you can see, the mathematician is all the way far on the right. So as you're studying science, you're probably noticing, right? Everything uses math. Math is a basis for everything that we do. And a very fun question that I often get is, okay, that's great. Do you just add numbers? Are you guys just looking for prime numbers? What do you do as math research, right? Everything's been discovered. We've had it for thousands of years. These are all the areas that you can do research in math. And they're actually even more to this day because it keeps expanding. So a lot of things are based on, that college algebra you took, that calculus course. It's taking it to an abstract level and kind of seeing what's going on in your mind and being able to apply it to spaces, that aren't just the real numbers. So don't worry, I'm not going to take you down this rabbit hole, but it's a very fun one. So what I do is I work in an area using functional analysis, differential equations, and then control theory to apply it to real-world problems. So my path is a little different. I went to math grad school. I was like, oh, there's all this really cool abstract stuff. You can do all this neat things with math, but I would love to see how that actually affects the real world. How can I take these really neat properties and change things and affect things? So we're going to look at a real-world problem and apply some math to it. So over in this corner here, this is a citrus plant. Okay? Everyone like orange juice, right? We just had breakfast. Okay? So what there are is in Florida, there are these little insects called Dapperus root weevils. And what they do is they take your beautiful citrus plant that looks like this and make the roots look like that. They eat the leaves. They just basically are infesting. They came over. It's our fault. We brought them from the Caribbean in the 1960s. And so they're an invasive species, and they're eating all the citrus fruit. They're getting taken to California. And so what I want to do is I want to figure out a way that I can help the farmers, right? I want to help stop the spread of this invasive species. So in order to stop something, you got to know your enemy, right? Everyone's seen lots of movies on that. So this is our little Dapperus root weevil. This is the little bugger that's eating all your oranges, okay? And I should say I'm a math biologist, so we're going to have a little biology today. You'll get more later, I know. But we're going to have a little basic to start with. So you start as an egg, you become a larvae, you become a pupae, and then you become an adult, right? So that's kind of our enemy. We know he eats leaves. And if we're looking here, right, a big issue seems to be the fact that if this little larvae is underground, it's eating the roots at the roots. So the larvae is the root of the problem, and we want to get rid of it. There's so many wonderful puns, don't worry. Okay, so I want to get rid of this larvae. But I want to be able to take all this information from the real world, right, and condense it. Because what I'm telling you right now is all the information, but that's a lot of words. And it's hard to communicate that from people. So we want a shorter language to communicate things. So does everyone remember the movie The Matrix? Yeah? It makes me realize how old I am when I teach, when I mention this, and all my students are like, what? Keanu Reeves? So the great thing about The Matrix, right, was at the end of the movie, we found out that this code, a sequence of numbers, characterized an entire universe. I can take everything, the colors of this room, all of it, and condense it just to numbers. And while it may look complex, right, that's a lot easier way to communicate things, because there's 0 through 9 in a specific order will tell me what's going on. So what I want to do is condense a real-world situation into a shorter thing that I can actually work with. So let's think about this. We had larvae, we had pupae, we had, eggs, and we had adults. So let's think of all the possible things that could happen in this system. All right, so here's a big chart. Don't worry, we're going to talk about it. So in this first row here, I could have an egg become an egg go to a larvae, egg pupae, egg adult. And then I have all the kind of ways you can transition from state to state, right? So a pupae, so what this means, right, is I survive. I stay as a pupae, I keep continuing being a pupae. But it does not really make sense that if I have matured to being a pupae, then I'm suddenly going to revert to being a larvae. Or if I'm a pupae, I'm going to revert to being an egg. So some of these just don't make sense, right? You could mature from the previous stage to the next stage, but we're not going to go back in time, all right? So in those cases, right, where this doesn't really make sense, where I can't really go back in the stages, or I can't have a larvae that's laying an egg, because toddlers don't make babies, okay? What I'm going to do is that can't happen, right? It's an impossibility. We're just going to put zeros. Can't happen. Not going to worry about it. So those are situations where it can't happen. I put zeros where it can't happen. But up here, I'm looking at a time step, right? So as the biologist will say, right, you can only record things, once a week. I can't sit there and constantly watch the bugs out in the environment. So I'm going to say once a week we go out and check what's happening. So after a week, some of the eggs are still going to be eggs. They won't have grown up yet, but some will grow up. Some of the larvae will stay larvae. Some will have grown up. So I can tell what's happening, right? And I also can figure out what ratio of eggs stayed eggs and what ratio grew up, and about how many new eggs I got from the adults. So those are numbers, right? I can just use the percentages. Congratulations, you all just made a matrix. That's all the matrix is it's telling me this is how many eggs are going to stay eggs. This is how many eggs now become larvae. So this matrix here is actually the basis for everything that I do because it's telling me the dynamics. It's telling me how do I move from stage to stage. So for instance, I know it's equations. It's going to be okay. If I want to look at how many eggs there are after a week, I look at the previous week, right? Because 0.3 of those eggs stayed there, and then 0.5 of them moved to the larval stage. So I can take this matrix and make it equations. Now there are a lot of zeros, and 0 times anything is 0. Lovely. So I really just have these nice 4 equations, and that's telling me all the dynamics about those Diprotodontus root weevils. Isn't that a lot easier than me showing a chart and describing it? We just have equations. So that's all math is doing, right, is it's putting stuff into language that's easy to communicate to anyone. All right. Well, we want to get rid of them, right? And we don't want to use pesticides. Pesticides are bad. They make food taste weird. So we're going to use nematodes, which is a little parasitoid. You can buy them. They will get here in 2 days via FedEx, if you would like. And you're going to spray them in your garden. And what they do is they attack just the larval stage, and they're not going to have any bad effects on the environment. So here is our orchard of oranges that we're saving. And we've sprayed some nematodes, and here are the weevils. So if you notice, a lot of times, right, we find the weevil, but sometimes we sprayed nematodes and there weren't any weevils, and sometimes we didn't even find the weevil. So there's a chance that you may not actually get everything, right? There's a probability of whether or not I'm going to encounter it. So am I actually going to run into the weevil with the nematodes that I want to get rid of? So when I put them in, I have to put a probability factor. So what that means, and we're starting to get a little mathy, I know. We got the larval here. All this E is doing is saying that's the likelihood you're going to actually find a weevil with your nematodes. So the more nematodes you put in, the more weevils you're going to get rid of. Okay? So at the end, this is kind of our system of what's happening based on how many nematodes and how many weevils there are. Now I said we're going to help farmers, right? And what do farmers care about? Money, right? Everyone's here to make money. We like money. We're trying to win money. So obviously everyone likes money. Okay? So what the farmer actually cares about is during a week, how much is this going to cost me? So the cost is, right, how much do I lose from my orchard? How much are these weevils eating? Plus, how much does it cost to buy the nematodes? So that's all I'm doing, right? I'm adding together how much you're going to lose, plus how much you have to pay for it. So all those things put together, so everyone feels good, right? We got the dynamics, we got the cost. What I deal with, this is just as like summarizing that into a few numbers and a few symbols. It's all that stuff you just understood, but it's writing here. This is how much it costs, how much you lose from your orchard. This is how much to buy something. This is how many weeks you want to do it for. And these are the dynamics. So it's one of those, this may look complex, but it's something that you can understand if you go through the steps of, okay, yeah, all we're really doing is making this matrix and talking about it. Now, if we want to solve this, right, we could say, all right, let's apply nematodes once a week. Let's apply nematodes twice a week, 3 times a week. Right? We can just guess and try and guess and check forever and ever and ever because there are many, many solutions. But here is where math comes in. So what I use is a thing called optimal control theory and functional analysis. So basically think of calculus but on steroids. Okay? So I'm going to use that idea of like trying to find a min or a max, and I can find you a control so I can tell you how many nematodes to apply in a unique way that exists with necessary conditions. So I can say using MATLAB, you should apply this many nematodes, and it'll only cost you then $1,000 to treat an orchard, as opposed to if you treat it maybe once a week for the entire year, it'll cost you $7,000. So that's the part that math comes in, is this idea of that if you set up this system, I can use math, right, use these functional analysis properties to solve it. So you saw a little bit of pure math, maybe enticed you to ask some pure mathematicians what the heck it is they do. Talked a little about applied math. There's fun math too. Watch Futurama. And then here's my little joke that I have with my mom, because she is not a mathematician, sadly, but if you've seen my Big Fat Greek Wedding, right, Give me the root of anything. Give me anything, and I will show you the root of that is math. And that's my talk.